Okay, so let's start on soft matter. So on day 1 and day 2, I was here and I asked you what soft matter was and if you could give an example, and you rightly said clay, right? But now who said that it was clay? Not here? No? Okay, doesn't matter. Okay, so now today, we'll find out whether clay is a solid or a liquid. So what do you think clay is? Is it a solid or is it a liquid? You've seen clay, no? Clay is basically the main ingredient of mud, right? So do you think it's a solid? So how many think it's a solid? How many thinks it's a liquid? Solid? Just a few tentative hands. Solid? Liquid? Nobody thinks it's a liquid. Okay, so let's see what it is. Actually, it's neither really, okay, or it's both. Okay, so that's what we'll find out. So my name is Ranjini Bandyopadhyay. I'm a professor at the Raman Research Institute. Sumathi told me that I should tell you a little bit about myself. So I have been at RRI since 2005, and I come from Calcutta. My father was a geologist. He was actually from the village. Okay, and my mother was a homemaker, but she really liked math, and she'd really make all the local kids learn math. So she used to give tuition sometimes. So we traveled a lot because of my father's job, and my mother would catch all the local kids and make them do math. Okay, and then I remember my father really wanted me to do the civil services, but I wasn't very interested. I came for the PhD interviews, okay, in ISC, and I cracked it. And then I joined, I wanted to do experiments, and then I ended up with Professor Ajay Sood. Have you heard of him? He's now the principal scientific something to the government of India. Okay, what is it? Advisor. Thank you. Yeah. So, anyways, so then I remember when I came to IISc in 1995. Okay, and this was way before Google or even Microsoft Windows, right? So you can't really find out what the options are, or forget about AI. There was no Google, there was no search engine. So then when I came here, when I came to IISc, I knew I wanted to do experiments, and all I had heard of was semiconductors. So I thought I want to do semiconductors. And then when I came to ISC, I found that everybody wants to work with Ajay Sood, that year. And then I found out that Ajay Sood wants to do, he does two things. One is, he uses Raman spectroscopy to look, at that time he was looking at these strongly correlated electronic systems, perovskites, and then after that he also moved on to nanotubes much later when I was still in the lab. And there was something else that he did that was called soft matter. And soft matter had something to do with, cosmetics and lotions and food and so on. So I thought I want to do that. And I did it. And then, now every time, I look under a microscope and I see bubbles of foam move, okay? Or, when I'm bouncing a ball, which we'll do today, I think, I really, I've had so much fun in my career. And so this is a kind of a talk that, I'll give you an overview of what the soft matter is. I'll also pass around some experiments and I'll ask you questions. Okay, so please raise your hands and please answer. Okay, and yeah, so okay. So so some of you said that it's a clay is a solid. Some of you said that clay is a liquid. Okay, and I said that it's actually both. Okay, so now you've seen clay, right? You've seen pottery, and clay is also a good. It's a very good insulator. It has all kind of medical benefits. There are all kinds of clays. Okay, for instance, there's a kind of clay called kaolinite that is actually used as treatment for diarrhea. Okay, so clay is the fourth most ubiquitous material that we know of. Okay, after air, water, sand. Okay, so now. So we have, and there are different kinds of clays, they all have the same structure. Now, do you know what clay looks like? So if we take clay under, if we just take clay, which is basically these, clay particles in water, and we look at them under a microscope, have you ever thought what it would look like? No? Okay, this is what it looks like. Okay, so this is what it looks like. Okay, so what you see here, so this is an image that we got in RRI. Okay, oops, wait. Okay, under an electron microscope. So an electron microscope basically uses the wave nature of electrons, and it generates images. So what you see here is a backscattered image. So you won't see it really, but these are tiny, tiny clay particles that are associating to form this kind of a network. It's called a gel. Okay, and the reason why this forms is, because of this forms because of electrostatic attractions. Okay, so there are, clay is a very interesting particle. There is a distribution of charges. It has positive as well as negative charges. So clay is really disks. Okay, these are, if you like chemistry, then these are aluminum silicates, and they have sheet-like structures. Okay, so they have aluminum, they have silicon, they have sodium, they have magnesium. So they have all kinds of, they are a kind of a mishmash of many different inorganic molecules, which, form this kind of a disc-like, plate-like structure. And yeah, and so they have plate-like structures, and just to, if you look at, if I just describe what a single clay particle looks like. So it's a disc, and it can have the diameter of the disc could be anywhere between 25 nanometers to 4 microns. Okay, and it depends on, you have all kinds of clays, smectite, kaolinite, bentonite, all kinds of clays. So the size of the particles and also the polydispersity, which is the standard deviation of sizes, depends on the kind of clay. Okay, so think of clay as a disc. I do not have a disc here, but anyway, it's a disc, and it has lots of sodium ions on the surface. Okay, so when you put a clay particle in water, the sodium ions are going to dissolve out, right? So now you can think of clay as a plate when you put it in water with positive charges. Okay, the positive charges that counterbalance come from oxygen ions that are on the surface of this plate-like structure, the sheets. Okay, now there's something else that very interesting that happens. So if you look at the clay particle, it's basically a magnesium a magnesium, there's a layer of magnesium, and on both sides of magnesium there is silicon. Okay, so now, think of magnesium as making a kind of an a structure in the middle of the clay particle. Okay, so now when you put this clay particle in water, the magnesium gets hydrated. Okay, so it forms magnesium hydride. So the rim of the clay, the rim of the clay disc, that is positive. So you have negative faces, positive rims of the clay particles. So if you have two clay discs, they form these house of cards structures. Okay, they can do much more than that, but today we'll just really simplify it and just say that they can form these house of cards structures, and when you have many clay particles, they can associate into networks that look like this. Okay, so this is, as you can see, this is a scale bar of 2 microns. So you end up with this very porous structure. Now we can change this porous structure by adding salts and adding acids and doing other things, but today we'll not bother about all that. Okay, because clay is kind of a poster child of soft matter. So I thought I'll start with this and then eventually tell you whether clay is a solid or a liquid, and if there are other materials that also have the same kind of mechanical response. And these are all materials that you know. Okay, it's all, I'm going to use material that you know, like polymer and cornstarch, and we'll do some experiments. Okay, so when you put a lot of clay particles in water, this is what you get. You get a gel-like structure. So these networks are called gels. But the structures are very weak, because remember, they are not held together by covalent bonds or by really strong electrostatic bonds, but they are held together by what is called a screened electrostatic repulsion. Okay, because a screened electrostatic interaction. So what happens is you have disks, and you have these, there are these ions that are kind of, leaving the disks, like I told you, the sodium ions. Now there are two things. So once the sodium ion leaves the disk, there are two pulls. One is that, the sodium ions get pulled back by the oxygen ions on the surface of the clay. That's one thing. The other thing is, the thermal, there's always thermal fluctuations, right? So thermal fluctuations try to kick the sodium ions out into the bulk. So these two competing forces give rise to a balance. And then if you look at a clay particle, you can think of that as a disk with a kind of an egg-shaped cloud of sodium ions around it. Now, when you have two clay particles with these egg-shaped clouds of sodium ions around it, they do not, remember the clay particles are negative really on the whole, I mean, the net charge is really negative, and then you have this, positive cloud surrounding it. So when you have two such particles that interact, they interact not by Coulombic interaction, but something called the screened Coulombic interaction, which looks a lot like the Yukawa interaction. Okay, so that is actually short range. Okay, which is why you end up with structures such as these. Okay, and because these are held together by these much weaker screened electrostatic interactions, these materials are what are called fragile. Okay, they have direction dependent interactions. Sometimes these materials are so weak that if you shear them along this direction, they can actually break along this direction. So if you really want to find out about the flow of these materials, you need to use tensors. Okay, which is again something that we'll not go into, but then you can think of this material as a very fragile material with this microscopic structure that is held together by very weakly interacting constituents, and all materials that kind of fit this definition can be called soft materials. Now we'll go deeper into this. Okay, so what is a soft material? Okay, and like I told you, these are very, very ubiquitous materials that you see around all the time. Foods, cosmetics, things that you use every day like toothpaste, jam, okay, it's all soft materials. And we'll tell you that, so we will come up with a definition later, and you'll see that, even though these materials are very diverse, right? They have diverse, they look different, they have different applications, but they all fit a definition that I'm going to give you after this. Okay. So what is then, so just, this is a kind of a very superficial definition. So I'm just saying they're all very soft, right? What do I mean? That they are fragile. And why are they fragile? They are fragile because they are constituted, they are made up of these very, very, of these supramolecular structures, okay? Not a single molecule, not single molecules that are really interacting, but you have to really look at, larger structures that are interacting, which are made by an aggregate of molecules. Aggregate of molecules are called supramolecules or macromolecules, okay? And it is these macromolecules that can self-assemble and they can interact through some very weak interactions. So that gel that you saw before, that's actually a very weak gel. If I make clay, okay, it could look almost like a solid, but you can actually just melt it, You can just, stir it with a spoon and it will start flowing like water, okay? So because they are so fragile, they are fragile because of these very weak structures that form them. I showed you an example in the last slide, but because the structures are so weak, they can easily be broken up. Okay, like I said, by a spoon. So what I have here, but this is really in a different context, this is cornstarch in water. Okay, this is cornstarch that you use to thicken soups. And here there is also, this thing called, there's a recipe for pista kulfi. Okay, so this is something that you see, ouch, and then you also you get it in the supermarket, right? So this is a good example of a soft matter. Okay, so if I just leave it standing, you'll see that it's becoming thick, but the moment I stir it, I can stir it. You can't do it with the table or the chair, right? So okay, so we are going to define a soft material as something that can behave both as a solid and a liquid on laboratory timescales. What do I mean by laboratory timescales? It basically, the short laboratory timescale is defined by, the kind of instrumentation that we have. We do light scattering, we do rheology, we use, we have optical tweezers, we do all kinds of stuff, we set up our own experiments, but the kind, the lowest timescales we can measure are about, say, 10 nanoseconds or so. Okay, so we can start from there as the relaxation, as the, the characteristic time scale of soft matter. And the largest scale is really set by the PhD tenure of a graduate student, which is like 5 years. But yeah, I mean, I'll get killed if I, ask them to measure a system which has a characteristic relaxation time of years. So, okay, so we work with systems, whose relaxation times are, say, between a few hundreds of nanoseconds and, say, microseconds. In some cases, it could be hours. Okay, what is a relaxation time? Do you know what a relaxation time is? So we'll just use a very, again, a superficial definition. So a relaxation time, everybody, everything, every material has a relaxation time, right? We'll say that that is roughly the time that you take to traverse your own body length. So I'm a meter, right? Roughly, we'll do approximations in height. So the amount of time that it takes me to walk a meter is my relaxation time. Now these clay particles, they are like, like I told you, they are about maximum, they are about 4 microns apart, but they are discs. So if you calculate their effective volume, spherical volume, it's like, maybe 100 nanometers or so. So the amount of time it will take for the clay discs to say, move by 100 nanometers, it could be, under an external shear, it could be, under thermal fluctuations, whatever, that is its relaxation time. Okay. Now these are of course systems that are completely out of equilibrium. Okay. So, and maybe we'll come to that at some point. So therefore, you cannot really define a unique relaxation time because that will depend on, the external forces that you are imposing. Okay. So now, why do I say that these materials are solids and liquids at the same time? At laboratory time scales is something that we've used so that, we can actually work on these materials. Okay, so a solid, as you know, has elasticity, right? So these materials have elasticity, and the elasticity comes from the underlying fragile structures, which I showed you. Now the viscosity, which is really a measure of the dissipation, that comes because you can easily break up the structures. Okay, so, and I don't know if I've been very consistent, but everything that is a solid-like or an elastic property, I've kind of colored it red. All the liquid-like, properties those are blue, and the typical, properties of soft material, that is in that greenish shade. Okay, so solids and liquids. So before discussing materials, that could be solids or liquids or both together. Let us try to let us try to go back to our middle school days and discuss what solids and liquids are. So here I have some examples. So can you just raise your hands, and I just want high school definitions. I don't want anything complicated. Okay, so what is a solid? Just raise your hand and tell me your name. And yes, you said something, I think. No? No? Okay. Yeah. Okay, what's your name? Drishti, thank you. Yes, okay, fine. Finite, fine, not finite, you mean a fixed volume and shape, I think, right? Yeah. Okay. Yes? You're saying it has to be ordered? Really? What about glass? Glass is you can have disordered solids, right? So you're right. I mean, so I think what you mean is that, they are rigid. They have rigidity, right? Okay, that's correct. Yeah, but you can have, so for instance, the window glass, this is a solid. Okay, this is a solid, but it is amorphous. But a rheologist will tell you that, it's really liquid. Because, as you know that liquids have disordered structures. So anyway, so glass is a soft material. Okay, so it's a kind of a gray area, but yeah, they are rigid. Anything else? Yes? For that rigidity, right? Okay, I'll take that. But it doesn't have to be that way because, again, in soft matter, they are not, but then they also, that is why they have a liquid-like property. So that's correct. Anything else? No? Okay, fine. That's okay. We have almost everything. So it's a rigid. Because it is rigid, it cannot flow, right? It retains its shape and volume. The atoms are usually packed tightly together. Okay, and to me, so I work on something called rheology, which is really the the science of flow and deformation of materials. So we talk in terms of energy. So solids store energy, okay, just like a spring does. Okay, and you know Hooke's law, right? So Hooke's law goes like this. Now in rheology, we basically see this K here, the spring constant, that depends on the spring, right? But then, we want it to become a material, a parameter that really, a material property, a parameter that characterizes the material. So we write the same Hooke's law in terms of stress and strain, where G is what is called the elastic modulus. Okay, and now, pictorially we represent it with a spring. Okay, so basically, you stretch it or you pull it, it's basically, it is elastic, right? I mean, the moment you remove the stretch, you're going to go back to the original configuration if it is an ideal spring. If you stretch a spring a lot, you attain what is called permanent set. It's not elastic anymore, right? So similarly, so I mean, this is how you would define a solid. This is like the definition. And so when we pictorially we represent a material, if it is completely elastic, you could represent it with a spring. Now, do all these materials, are they perfect elastic solids? No, right? They are not. Metals are. Okay, metals actually are very good elastic solids. Anyway, now what are liquids? Okay, so here are some examples. Okay, so you have olive oil, you have water, and glycerol and stuff. They are all liquids. So liquids basically do everything pretty much that solids do not, and those are the definitions that I've chosen. Okay, liquids flow. They take the shape of the container. They retain their volume but not their shape, right? And they dissipate energy. So just like a spring would store all the energy, liquids dissipate all the energy. Okay, and you know Hooke's law, but do you know what the law is for liquids? Hmm? They don't teach it in college, no? No? Okay, so that's called the Stokes-Newton's law. Okay, so that's called Newton's law of viscosity now, but apparently Stokes also had a hand in it, but then his name somehow just vanished. But then just like for an elastic material, stress, strains, right? Hmm? The right deformation divided by the length scale, that is characteristic of the material. So just like in the case of an elastic material, stress is proportional to strain. In the case of a liquid, like an ideal liquid that you see here, stress is proportional not to the strain but to the rate at which the strain changes. Okay, and just like an elastic solid is pictorially represented by a spring, a liquid is represented by this element that is called a dashpot. Okay, you have heard of a dashpot? Okay. Mhm. Right. Right, right. Exactly, that's great. Because now there's an emerging field of study that's coming up that's called soft earth geophysics. Because earth is really probably one of the nicest soft material that you have out there, right? So yes, so that's great. Yeah. So a dashboard, by the way, I mean, so what's your name? You're from? I say Pune. Okay. Okay, so I'm really glad they're teaching you all this. Okay, so a dashpot is basically a pot of water. Okay, water dissipates, right? So so you see, this is like the water, this purple material here, or some, very dissipative material, liquid. So here, suppose you have a piston, okay, and you apply mechanical energy on the piston. What happens to the water around the piston? Is displaced, right? It will start flowing, right? It will flow around the piston. So the energy that you are giving to the piston, that is being completely soaked up by the water, right? So therefore, this is dissipative because it is just immediately it loses all the energy. This is a dissipative process. Okay, so solids are rigid, liquids are dissipative. Solids are defined by something called an elastic modulus. Liquids are kind of defined by something called a viscous modulus. And as you know, this is viscosity, right? So in this Newton's law of viscosity, the proportionality constant is the viscosity. What does viscosity measure? Viscosity measures the resistance to flow, right? So basically water, as you know, do you know what the viscosity of water is at say around room temperature? Or 20 degrees is nicer because the number is nicer. What is the unit? Somebody said Pascal second. Who said Pascal? It's correct. Correct, right? Actually, the viscosity of water at 20 degrees is around 1 millipascal second. Okay, so right, but then if you take glycerol, glycerol is a lot more viscous, right? So basically its viscosity of glycerol is much higher than water. Okay, so that's solids and liquids. Now soft matter is both, and here are some pictures of soft matter. Okay, so now let's just think of these matters as, let's think of the solid-like and liquid-like properties of these matter. So what do I have here? I have sand, right? So why am I calling it a solid or a liquid? Can you tell me a situation where, sand is a solid? Beach, you can walk on sand, right? That's a solid. I can't walk on a liquid, okay, unless you're some superhero, right? But I mean, you can walk on a beach and it seems to be solid, right? But then if I take the sand in my, hand, and if I separate my fingers, sand flows, right? Why does sand flow? Because unlike the table, okay, sand, the interactions between sand, they are just frictional. Okay, so the moment you give more space to the sand particles, they can all go here and there and here because of gravity. They're just actually, they are pouring out because of gravity, and they pour out like a liquid. Okay, so there's been a lot of lovely research on, granular jets and stuff like that, where, grains of sand behave like a liquid. But, technically, I mean, when you walk on the beach, we think sand is a solid, right? So just tell me one thing. This is going to be one of those, have you noticed kind of talks. Okay, so I was telling this to our TA Adeshbir here about, he's going to go to Goa. Okay, so if you guys ever go to the beach, or if you've already gone there, you can tell me what happens. So, so suppose you go to the beach very early in the morning. Okay, have you noticed that the beach sand is wet? Now, if you walk on the beach, okay, you'll find that your feet, with bare feet, you'll find that your feet are not very, uh, they're not as wet as you think they should be. Have you noticed that, anybody? And you'll also see that the sand is coming on top of your foot. I mean, if I walk on a table, the table will not come on my foot, no? But if you walk on wet sand, you'll see that, the top of your foot is also messy. It's filled with wet sand. Now, why does that happen? So there are two things. Why do you have sand on top of your foot when you're walking on sand? And the other thing is, why does your foot not feel so wet? Okay, so notice all this, and my job today is just to show you that there is some real cool physics, of course, in the beach and also in your kitchen. Okay, so notice it, do experiments, it's a lot of fun. Okay, so now why does sand behave like that on a beach? Because sand does something, it dilates. Okay, this is a procedure that's called, this is a phenomenon that's called Reynolds dilatancy. Okay, it dilates as it swells. So if I put some pressure on sand, which is the weight of my body, sand actually dilates. Okay, so because the interactions between sand are very weak, right? So so it is just a property of sand, okay, coming out of the very weak frictional interactions that the particles share among themselves. So when I put my body weight on the wet sand, the sand actually starts swelling, and that is why it lands up on my foot. But as it starts swelling, it's also leaving lots of voids, right, in between the sand particles, and the water just, drips in through those pores. Okay, so when you find that your foot is actually rather dry, it is not an accident. There's really something that's happening. Just the the action of your walking on it is basically making the sand swell, and the water is just going underneath. Okay, it is just going through the pores to the bottom of the sand, or as far down as it can go. Okay, liquid crystals. We have it on our laptop screens. Okay, and why do I call it a solid or a liquid? So liquid crystals are basically, they are like cigar-shaped, angstrom-sized molecules. Okay, and usually, they'll in a what is called a smectic phase, or a nematic phase, they'll have orientational order. Okay, in smectic they also have translational order, right? But so you can think of all these particles, these little cigars that are kind of oriented in the same direction. Okay, but the moment you put like nanovolts, okay, they start rotating, right? And these are birefringent materials. So your computer screen here has two polarizers, okay, and this very thin layer of liquid crystals. So you see the colors. Okay, and the way why LCD screens are possible is because of the fact that you need very small voltages to flip these particles. The other thing that you'll notice about soft matter is that you cannot really talk about one particle. You'll only be talking about an assembly of particles. Okay, we'll come to that later. Okay, so the elasticity of these materials arises from the underlying fragile structure and the viscosity from the breakdown of these fragile structures. So I have some more pictures here. Paint, right? Paint is soft. How many of you thought that paint was a liquid? Many of you would have thought so, right? But if paint was a liquid, it would be a pain. Why? Because you paint your wall and it will start flowing down, no? So therefore, when you make paint, which is essentially pigments and some polymers, it is actually a soft material. That's why you can make non-drip paints, because paints are made in such a way, okay, such that, when you paint the wall, they start flowing. So you have a brush, right? So you just take the paint out with your brush and then you just, paint the wall, it flows nicely. So this is a material that does something called shear thinning. So when you're applying a shear, its viscosity goes down. It can plunge by orders of magnitude, okay? But the moment you remove your brush, there's no shear rate, right? So then it just goes back to its original viscosity. So this is what is called a thixotropic material. Okay, so just like you can thin under shear, you can thin a material under shear, polymers do the same thing. Because if I, like plastics, okay, so think of these as long chain-like molecules in water, say. Okay, now if I, polymers, if I shear polymers, so when I'm not shearing polymers, these chains, they all entangle under thermal stresses. Right? So the same thermal stresses, that end up entangling these very long chains can also disentangle them. So polymers are actually always constantly entangling and disentangling. But when you apply a shear, you know what a shear is, right? You all know what a shear is. So when you apply a shear on a polymer, then all the polymers, they all disentangle under the shear and they all line up under the, along the direction of flow. Okay. So if you look at the viscosity of polymers under a shear rate, shear rate, right? I just showed you. So viscosity of all shear thinning materials would look like this. And this fall can be orders of magnitude. And a lot of work actually goes in, okay, in designing materials that do this. Okay, so that's about just shear thinning materials. Now here I have some food, and well, this is not really food and neither is this, but these are all materials you've used, right? So this is tomato ketchup. So when you pour it, does it come out easily? You have to smack it, right? See? So I mean, people do research on that, because when Hindustan Lever or Maggi is selling you tomato sauce, they'll try to make sure that more of this tomato sauce comes out with a smaller smack, because then you'll use it up more, right? So this is actually like a an industry that is, a lot of money goes into it. And I should also tell you here that before I came to RRI, I actually had I had an offer to join Hindustan Lever, okay, and I was to work in a toothpaste, in the toothpaste part, okay, of their company. And again, toothpaste has the same characteristic that toothpaste, doesn't come out on its own, right? You have to squeeze it. Right? Yes? So that's interesting, right? Because this is why. Because these are all materials that are formed with these soft materials. These are macromolecules. These have these fragile structures. In the case of toothpaste, there's also clay, by the way, because it's a very good kind of a lubricant. Okay, so it gives you that nice, that feeling, that texture when you're brushing your teeth. Okay, but these are very complicated. They have underlying structures, but these are very weak structures. So when you smacked your tomato sauce, or when you squeezed your toothpaste, what you did was you gave it the stress to break that structure. So then immediately your toothpaste will start flowing out, as will your tomato sauce. But the moment you stop smacking your tomato sauce or you stop squeezing the toothpaste, it doesn't come out anymore, right? What that tells me is that that little stress fluidized it, it made it flow like a water, flow like some liquid. But the moment you stopped squeezing it, it went back to its original configuration. Okay, so and why does it go back to the original configuration? Because these are materials that are usually held together very weakly, either by hydrogen bonds or by these screened Coulombic interactions. There could also be capillary interactions, as you'll hear in the next talk. Okay, so same for the jam, right? So so when you take jam on your toast, right, and you just take it, scoop it out with your fork or with your knife, and it sits like this. No, this is a solid, right? It's maintaining its shape and volume. But the moment you use your knife and you spread it out, it just flowed to occupy your whole toast. So what you just did was, you went from a solid to a liquid, but not by changing temperature, by using a mechanical force. Okay? Yes.
So one day I opened it using benzoyl peroxide, and when I opened it, it came out automatically without even squeezing it. Like it just started coming. And when I closed the cap only, it like I have to close with the cap.
That I don't know why that happens. Because benzoyl peroxide is not a soft material. I don't know. So maybe, I'll have to find out. I'll have to do Google AI, which I couldn't do earlier. But this I don't know. But thanks for letting me know. Yeah. So okay. So this property of many of these soft materials, where they behave like a solid under no force, but then they start behaving like a liquid when you put a little amount of force, this is called an yielding behavior. And the stress that you have to apply to make these materials go from solid to liquid is called an yield stress. And some materials are shaving foam, tomato sauce, toothpaste, and shaving foam, right? First get out this. So solid, right? Liquid, right? So soft matter. And why do you think, okay, there are two things. Why do you think, we are doing all this? I mean, what use is this? What do you think foam, what do you think the shaving foam is made of? Do you know? Louder and, it just, huh? Gas bubbles in water, great, yeah, true. But it's not just gas bubbles in water, because gas bubbles in water would pop, right? They would all burst, no? The bubbles are of colloidal size. You know what colloidal size is, right? I mean, that is not something that I was planning to cover. But basically, a colloid is some material, okay, which is stable under gravitation and the diffusive flux. Okay, so that is a colloid, and if you work out the length scale, the size of the colloidal scale, length scale, is anywhere between 10 nanometers and a few microns. Okay, so if you look at the bubbles in this material, the shaving foam, those are all about a few, well, I mean, my first postdoc was actually on Gillette foamy. So those are really, they start off at around about 50 nanometers, but then, this is what is called an aging material. So, the foam actually changes with time, because it is gas bubbles in water, right? So the gas bubbles are much lighter than water, right? So foam is technically, it cannot be stable, because the water is just going to settle down and the gas is going to just it's just going to kind of disappear, vanish, right? But foam is stable. So you're right, it's liquid bubbles, it's gas bubbles in water, but you have to make it stable. So do you know how you can stabilize an interface? You have to decrease the surface energy, right? So how do you do that? Surfactants? You have heard of surfactants? What is the most common surfactant? It's detergents. What we use to wash our clothes, right? And what is the speciality of these molecules? Do you know? They're not like, they're not really ordinary molecules. Okay? They form micelles. Why do they form micelles? What are micelles? Yes. So these are molecules or macromolecules which have one part. So you can think of them as a two-part molecule. One part likes water, the other doesn't. Like she said, the polar head likes water. The non-polar part is usually like some hydrocarbon group, so it does not like water. So when you put it in water, then the hydrocarbon parts will try to stay away from the water, right? So when you put many of these molecules together, they form what are called micelles. Okay, so you have one part that loves water, you have one part that hates water. So when you put many of these molecules together, they can form micelles like these. It is not a planar structure, this is a spherical structure. You can also form worms like this, okay? So you can form membranes, like we have in our cells, okay? So these are all, our life is made of surfactants. So you put surfactants, so when you're making foam, you have to put a lot of surfactants, because what do these surfactants do? They reduce surface energies. So surfactant comes from the name surface active agent. Okay, they reduce the interfacial tension. That is why, I mean, if you keep that Gillette foamy, eventually all the bubbles will pop. But it is, of course, also under a compressed, in a compressed environment. So they do not, they basically, that increases their shelf life. Okay. So, okay, but why are we looking at bubbles? I just told you, why are we looking at foam? That, my first postdoc was actually looking at Gillette foamy. Okay, and I was being paid by NASA. Okay, so what use do you think, NASA would probably, could possibly have of foam? I can tell you what we were doing, okay? So like I told you, in a foam, okay, the water part and the gas part will separate, right? Right, under gravity. But the idea of these experiments was to make a device so that, we could stop drainage. This is called drainage, the separation of the water from the gas, okay? And where can you actually reduce gravity? By taking your foam on a parabolic flight. Okay, so we were basically making a device to measure the rheology or measure the flow and deformation of these materials under different Gs. Okay, but so what? Okay, it's good for Gillette because they can increase the shelf life of their foam, right? But there's something very interesting otherwise also, which is that, do you know how the bubbles, so the bubbles are colloidal, right? So they will, they can move under thermal fluctuations, but do you know how these bubbles move? They move by something called stick and slip. Okay, so this is a very dense system, right? I mean, you have lots of bubbles that are kind of, jam-packed together, like in a very crowded bus. And when you're in a crowded bus, you can't move. Why? Because you're kinetically constrained. There's no place for you to go. But then the bubbles, we are almost incompressible. But bubbles are not. They're just gas, right? So they compress, they deform, okay? And then that builds up a lot of stress. And remember, where is all this coming from? Also, remember the bubbles are also growing in size because, the water, dissolves in the gas, right? So there's a lot of transport that's happening within the foam, okay? So now there's a lot of stresses that these flows are generating. So the bubbles are kind of squeezing against each other, they are deforming, they are changing shape, and at some point when a critical stress is reached, they all rearrange, okay? So if you look at the stresses on the bubbles, okay, with time, it looks like this. It's like a sawtooth. Now, this has been done to death. But do you know what this, sawtooth, where else you get this sawtooth movement? Much, yes? Excellent. Earthquakes. Okay, so earthquakes do slip. So the tectonic plates are really doing stick and slip. Okay, so this is like a lab scale experiment of earthquakes. Okay, what's your name? Sangeeta. Okay, very good. Have you done soft matter? Lovely. Yeah, you should watch YouTube, So there are some, I mean, you guys know this better than me, right? There's Veritasium and YouTube, and there's another very nice site called 60 Symbols. Huh? The fantastic stuff. I mean, there's a lot of wrong stuff, but experiments don't lie. So, there's some really wonderful resources on the internet, right? So let's see. Okay, we move on. Now I've lost this thing. Okay, here. Okay, so that's the thing. So that is what a soft material is, Soft materials are available everywhere, right? But they also serve as laboratory models, laboratory scale models for much, much bigger incidents. They also serve as scaled up atoms. Okay, because like I told you, these are macromolecules, which means that they are an aggregate of many molecules. So they are really like scaled up atoms. So people use these, colloidal particles to look at phase transitions, to look at glassy physics and many other things. We in fact look at glassy physics. Okay, so now there's another thing that's very important. There is a because of these fragile structures, there's a very strong correlation between the structures of these materials and their dynamics. Okay, What that means is you can, to these materials, if you give a small force, you'll get a disproportionately large response. Okay? So small forces, very large responses. And as diverse, these are very diverse materials, right? They look very different, but their flow and deformation exhibit some very universal features that can be explained by some common rules. Okay? So that is really what we work on. It's called rheology. Rheology comes from the word rheo, which means to flow in Latin, and logica, which is the study of. So the flow and deformation of these materials. Okay? And the simple principles that kind of govern them. Okay? So now, who knows about the pitch drop experiment? So now I'll show you that, pitch is a soft material. Okay, and to show you that, I'm going to tell you about one of the most longest running experiments in history. It's been going on for 96 years. Okay, so do you know the pitch drop experiment? Have you heard of it? You have heard of it, right? So let me tell you the history of the pitch drop experiment. Okay, maybe I'll not show you this because it gives you an answer to a question I'm about to ask you. So this person is Professor John Mainstone. Okay, so he was in the University of Victoria in Queensland. Okay, and he actually passed away a few years ago, but he was the custodian of this experiment, which was called this pitch drop experiment. Pitch as in, the material over which you drive your cars. Okay, that's a solid, right? I mean, we are driving over it. If it's a liquid, I mean, you can't drive on it, right? So let's see. Why am I calling it a liquid? Okay, so now, so this experiment was started in 1936. Okay, 1926, I'm sorry, by the professor at that time over there called Thomas Parnell, okay, who was trying to teach the students about viscosity and mobility and all that. Okay, so he took, all kinds of materials and he was showing how they flow, how viscosities differ from sample to sample, and he took pitch for some, he really had, a very good physical intuition that this would be a liquid, but it's a slightly, different kind of a liquid. It takes much longer to flow. And what is the experiment that Professor Thomas Parnell started? He took this, this bell jar, and inside he took this a funnel. Okay, and initially the stem of the funnel, this was sealed. Okay, and he poured in it pitch. Pitch is nothing but it's a mishmash of different kinds of polymers and tar and all that. Okay, and but then initially it's a solid, right? But then when you heat it, it becomes liquid. So they heated the tar or the pitch and they put it here, and then they sealed the stem for 3 years. That is till 1930. They waited for the pitch to kind of settle down. Okay, and then they cut the stem. Now, after they cut the stem, see, had it been a liquid, had it been water, the water would have flown out, right away. But then pitch also flows out, and you can see the drop here, right, that has formed. Okay, so can you guess? So now the experiment has been running now for about 96 years. Okay, can you guess how many drops of this pitch have fallen? Do you know? It came out in the newspaper, but that was probably when you guys were in, I don't know, junior school or something. Because the last drop came out in 2014. Now the next drop will come out anytime now. So this is a pilgrimage that I'd like to undertake. But anyway, so the picture that you see here, this is from 1990, 2 years after the 7th drop fell and 10 years before the 8th drop fell. So it takes about 12 to 15 years for a drop to fall. Okay, now there are some very interesting stories here, and I think if I don't finish it in this session with your permission, I'll go on to this, and so I will continue with this after the coffee break. So initially, of course, there were no CCTV cameras. It was too expensive, right? And then they put CCTV cameras in 2012. Okay, and then when the drop had built up, it had become quite big. Now when I've forgotten who was there. There was a different person who was kind of the custodian of this experiment. But then, this person had to go to the restroom. There were CCTV cameras, right? So everything is getting recorded, but the CCTV cameras failed. Okay, so as of now, nobody has seen these drops actually dropping, actually, detaching from the stem and falling down. Okay, but yes, there have been about 9 drops. And this seems crazy, and like, why should anybody be doing this for 96 years? But then it gives us some very interesting results. So what they did was, so now the flow rate of the drops, right? And Parshally's law. And by looking at the flow, the volumetric flow through the stem, you can actually calculate a viscosity of the pitch. It actually has a finite but a huge viscosity. And what is that viscosity? 2.3 into 10 to the power 11 times the viscosity of water. Okay, so pitch looks like a solid, but when you wait it for such a long time, it behaves like a liquid. Okay, so solid and liquid, it's all like some Maya. Okay, if you wait long enough, any solid will behave like a liquid, just like a liquid will also be a solid. Okay, and why do I say this? Can you give me an example of a liquid behaving like a solid? Platform diving in the Olympics, right? If you don't, so basically you have to go in. So you're jumping from that height, right? It's very scary to me, honestly. But then when you go in, you have to go in at a speed that is slower than the speed of the water molecules rearranging around your heads. Because if you go in at a, like a crazy angle, and if you go in very, very fast, the water is like a concrete block because it responds like a solid. So you can have a concussion. Okay, so think about how a solid can behave like a liquid. Okay, that's the homework. Okay, but there are many instances. Okay, so now a liquid can behave as a solid as long as the time scale of measurement is very short. Similarly, a solid can show liquid-like response if the measurement time is long enough. And it seems crazy, but it came up with this brilliant number, and it got the Ig Nobel Award in 2005. Okay, so I don't know, but soft matter has, what the Ig Nobel Award is, right? It is not the Nobel Award, but so these are given every year to experiments that first make you laugh and then they make you think. Okay, so this is one experiment this is one experiment that got so soft material experiments have got many Ig Nobel Awards over the last 15 years. Okay, so this happened in 2005. And then do you know about the viscoelasticity of cats? Huh? Have you seen that paper? So there's this very cute paper by a bona fide scientist who showed that a cat can be a solid or a liquid. Why? Because cats can get into any spaces, right? And also they and they can jump up like springs, right? So that's solid and liquid. And what Fardor did was that he also calculated typical numbers, which we'll calculate after dinner tonight, which are like the Reynolds number, the Deborah numbers, and all kinds of, dimensionless numbers that we use to classify soft materials. Okay, there's another one. There's another Ig Nobel that I know of, and that I know of, very, very intimately, because this is one friend that I have who actually got this award. Okay, so his name is Professor Gregory Weiss from University of California, Irvine. And you know why he got a Nobel Prize? He unboiled an egg. Okay, so egg is nothing but polymers, right? And when you heat it, those polymers get congealed. Now he's a chemist. Okay, he's actually a biochemist. So he showed through experiments that you can actually break up that congealed mess of polymers and you can go back to the unboiled state. Okay, so he got the Ig Nobel, I think in 2018 or something. Okay, so anyway, so and there are some very nice TEDx talks. There's one by Greg, for instance, on how you can unboil an egg. So initially when he got the Ig Nobel, he just unboiled the yolk, and now recently I found out that he's also unboiled the white. Okay, but these are basically all proteins and polymers and fats, right? So they are all colloidal stuff. It's just that they congeal very easily just by physical processes. They are not chemical really. Okay, if it is chemical, they are irreversible. You cannot, if boiling an egg was a chemical change, you wouldn't be able to reverse it. Okay, okay. So now, okay, so much for soft matter. I think I've only gone through about 1/3 of the talk, but how do you define a soft matter? I've given you all kinds of very random definitions. Now it's very easy because somebody got a Nobel Prize for finding out, okay, that the same mathematical treatment that you'd give superconductors or magnets can actually be used to understand soft materials like liquid crystals as well as polymers. Okay, and this is the this is the mathematics of something called an order parameter. Okay, and this person is Pierre Dijen. Okay, he passed away recently, and this is the first, couple of sentences from his Nobel lecture. What do we mean by soft matter? Americans prefer to call it complex fluids. This is a rather ugly name which tends to discourage the young students, but it does indeed bring in two of the major features, complexity and flexibility. Okay, and the reason why these are marked in green in a different color is because these are very, very important words. And what do we mean by complexity? We mean complexity in structure, macromolecules, as opposed to the material being composed of just molecules. Okay, now what are macromolecules and why are they interesting? Okay, so you know that many years ago, like 120 years ago, people were talking about single ions and single atoms, right? Now we are talking about, and this is soft matter is kind of a new branch. But here we are talking of millions and millions of atoms that are aggregating to form like a macroatom or a macromolecule, and we are talking about the interactions between those macromolecules, right? So just like life evolved from a single cell, right? And then now you have me, right? So similarly, physics, it will basically it gets more and more complex, and here we are talking about complexity of structure, right? So these are many molecules that are making the unit cell, the unit, okay, which is this macromolecular unit. Now what is flexibility? So now I told you this and I showed you with the form, right, that a small force on these macromolecular aggregates can result in a disproportionately large response. And actually when Dijen was giving his Nobel lecture, he actually told a story, and that was the story of the Native Americans in the Amazon basin, okay, and about the boots that they made, okay, which were made with a soft matter. And what was that soft matter? That was latex, rubber. Okay, so how did they make these boots? The Amazon, of course, has lots of trees. Well, the number of trees is declining, but there are lots of rubber trees. And how do you take rubber out? So within the trees, within the bark of the rubber trees, the rubber flows like a liquid. Okay, so what they used to do is they used to tap the bark of the rubber tree and the latex used to come out, which they would collect, and then they just take the latex and they just paint their feet, and lo and behold, within about 15 minutes or so, that liquid like latex became a solid like boot. Okay, do you know why it happened? Can you guess why it happened? Because oxygen in the atmosphere is way more reactive than you would ever believe. So what they do is latex is again nothing but polymers, so chains. Okay, now what happens when so in the bark it is not really exposed to oxygen, but once you take it out of the bark of the tree, they start interacting among each other and they start joining at specific nodes. So the latex, the rubber, which was like chain like macromolecules in the tree, the moment you bring them outside, they all kind of combine and they kind of they make these networks, and a network, as you know, is rigid, right? So oxygen did a reaction here which actually gave you a liquid to a solid transition. Okay, but this is just a simple chemical reaction, right, at the same temperature. Okay, so that is what is the flexibility. Here we are talking about the mechanical flexibility of these materials. Okay, so have you guys heard of Charles Goodyear? So you've heard of Goodyear tires? Probably not. Goodyear tires was when I was a kid. Okay, so Charles Goodyear came up with this concept of vulcanization. Okay, so this is just oxygen with latex at room temperature, right? But when you take, and you get these rubbers, by the way, these rubber boots that the Indians, I'm sorry, politically incorrect, the Native Americans would make, okay, they would also dissolve. Okay, because the same oxygen that built the connection also ended up severing these connections. Okay, but then that's a really bad boot, right? I mean, there are lots of leeches in the Amazon basin. So so it just stays, so the shelf life is very small. So one thing that they keep doing in the industry is increasing shelf life. Now, Charles Goodyear serendipitously tried to make a rubber with good shelf life. And what did he do? He came up with this process of vulcanization, where he basically boiled, okay, latex in sulfur, and that gives you rubber that is used in tires, rubber tires, right? And those stay, right? Those stay forever. So mechanical flexibility. Just do a little thing and completely change the property. Okay, so these are materials that can be engineered very well. And so I am just talking, this is a popular talk, but these materials and some of these are happening in my lab. Okay, I will tell you about the sensor part in the next session. They make these for soft robots, where actually even we've done it. We've made, two layers of, colloidal layers of different stiffnesses, but these layers also respond to changes in temperature differently. So when you put a temperature across these, two layers, they can actually curl, and they are like micro grippers. Okay, but these are tiny, right? Because these are colloids. So you can actually pick up tiny, tiny things. And that's why we are calling it a soft robot. So these are micro grippers. They're also adaptive material. They're also self-healing material. So if you break them up, they can actually reassemble right back into the original conformation. Okay, they're adaptive because small stresses can really make them behave very, very differently. And that is what you need in an industry, right? You need things to be versatile. Okay, so that's why we study these material. Now we'll start with the experiments, and this is the same cornstarch that you see right here. Okay, which is now, okay, we'll have to, okay. So what I have here, so so Iqbal, he gave me about this much of water, and I just took the cornstarch and I just kind of just to save time, I just kind of mixed it and then we stirred it. Okay, but before I pass this around, I'll tell you. So this was an experiment done in my lab. So this black thing that you see here, this is a speaker. Okay, a two-in-one speaker. It's an audio, a part of an audio device, and you just play some loud music on it. Okay, and what you have here is a petri dish with the same material, cornstarch, and then we vibrate it from below. Okay, so watch. Can you see the, let's stop it there. Okay, it's not stopping. Can you see the Faraday ripples? Can you see the ripples? So here cornstarch is behaving just like a liquid, right? You see ripples on the ocean, right? When there is the, some wind blowing on it. And then what Prakhyat, my student, has done is, he just, blew a hole, okay? He just blew air into the cornstarch. So what happened? He made that little hole there, right? So at the border of that hole, the cornstarch concentration became very, very high. And then cornstarch started behaving like a solid. Okay, so cornstarch is a fantastic material because if you apply very small shears to it, okay, it behaves like a liquid. But if you apply very large forces to it, it's the same material starts behaving as a solid. And that is what you will see here. So by the way, we call these cornstarch monsters, and I'm not going to make you suffer through this, but this video is actually of 20 minutes. It just goes on. So as long as you keep this Punjabi music going, so yeah, I mean, people were actually complaining about us that, I mean, just stop this. But, we needed a vibration, and here that was audio. Okay, so this goes on for 20 minutes. Okay, and it would have gone on for longer. Okay, so now, and this is something, so this I just got off YouTube. So this is again, and you would have seen it on YouTube, right? People running on a cornstarch pool. Here it's a cornstarch bucket. So like granular media, cornstarch also dilates. It is what is called a granular medium. Okay. So you see, if you go down slowly, you go right in. Okay. And then you can do this and you can still, kind of dance in it. But when you do it very fast, you're getting stuck. And now they'll actually put in some more cornstarch so that this effect becomes more prominent. So they've just put some more and, they're shoveling it in, making sure that it mixes nicely. So you can see it almost looks like a solid, right? You can pull it out, huh? And then it just falls down under gravity. It just breaks apart, and because it's also a very fragile structure, right? So it breaks very easily. Huh? So there used to be a cornstarch pool in ICTS, it was a source of a huge mess. But there was a cornstarch pool, so like a big tub. So people used to go and, get all messy and get out. Okay. Okay, so now they're going to jump on it. But the moment you stop jumping, you'll, go right in. right? And then with the moment he stops, so what did you notice here? That when you're applying a force on it, it's a solid, right? But the moment there is no force on it, it's a liquid. Why does that happen? I'll tell you something. I'll also pass around the experiment, but we will measure these time scales after dinner today. Yes. Quicksand behaves in a similar way, yes. Actually, we tried, these were failed experiments, but we tried doing these experiments with quicksand. Quicksand is again very interesting. So you're right, but quicksand is ulta, it's opposite. Because quicksand, if you're not applying any force, it behaves like a solid. But the moment you apply a force, okay, it actually thins. So that's why, have you read The Hound of the Baskervilles? Right? So the guy basically, he sank, had he just he could have floated because quicksand is, 70% water. You can float on that because so are we, right? But the moment you start, panicking and you start, flailing your arms and legs. So what quicksand has is this, this kind of very delicate network of sand. And the moment you're flailing your arms and you're panicking, what you do is you just break all the sand. So all the sand networks, and then you sink right in, but the sand will come, and there's also some clay, right, which is also forming networks. And then the sand and the clay, they all come and close in on you. So you're basically drowning and then suffocating. Okay, so experiment with cornstarch, but silently, don't move. Okay, then you'll be fine. Okay, so this is that cornstarch, and I'll start passing it around from here. So this is what I want you to do. Maybe you can just help me with this. So so this is just about, say, 60% cornstarch from the supermarket and 40% water, which we made earlier this morning. And what's your name? Isha is going to do an experiment. So she's first going to, stir this very, very gently, and then she's going to stir it really fast. And tell us, Isha, what you see or feel. Okay, and then we'll see why the rheology of cornstarch is like that. And you can just, pass it around. So we'll go like this. You can maybe stand up so everybody can see it. So gently first, and then, hard later on. It's easy, right? Yeah. So when you're stirring it gently, it moves easily. But then try going, doing it really hard. It's very difficult to stir. Okay, so you can pass it around, and we see. I'm sorry, I left out the first row, but anyway. So yeah. So we will see why this happens. Huh. You have to. I think other people will not be able to hear you.
A lot of people put cornstarch in ice cream
Right.
to make it like
Thicker, right? Yeah. Cornstarch is it's same thing in soups, right? So this thick soup that we have in hotels, they're just putting cornstarch. So cornstarch again, I'll show you. Let me show you what. Again, I keep losing this. Cornstarch looks like this. So and then we'll see why it behaves. Why you can thicken soups and ice creams. So this is again, so cornstarch, well, not from a supermarket, but from a company called Sigma Aldrich, but it's the same thing seen under an electron microscope. Okay, and this is what it looks like. So I don't know if you can see the scale bar here, but cornstarch particles, these are these irregular particles, okay, about 15 microns across, 15 micrometers across, and what they have, and the reason why they use as a thickener is because these have very rough edges. So, and they interact through friction. So when, when cornstarch particles come very close together, they just basically lock. And that is what, and then they can form a network, and that gives rise to this thickening behavior. And it's okay to put it in food because, it's edible, right? But then people also put a lot of trash, like, urea and all that. So that one has to be careful about. That I'll show you in the next talk. Okay, so if it is cornstarch, it's okay, right? So this is what cornstarch looks like. Now, your name? Drishti, I'm sorry, bad memory. I have a very porous memory, like my viscoelastic materials. So you see it, right? Huh? So why does this happen? So now you can see that these are discs. These are discs, right? Huh? So what is happening is when you're stirring it very gently, all the discs are aligning along the flow. And when things align along the flow, what happens? They can flow easily. No, they just go round and round, or they just follow the flow. But if you stir it very high, very, very strongly, then all these, these particles, they are all jamming into each other. They are all crushing and dashing into each other, and then they get locked. Okay, but again, this is just friction, right? So the moment you remove the force, they again fall apart. And that is what you're seeing when you do that. Okay, so now who reads or read Dr. Seuss? Yeah, do you remember this? So, so there was this guy called Bartholomew Cummins. Okay, so Oobleck was the name that was, actually given for cornstarch by Dr. Seuss, It's his, he came up with this. Okay, so there was this green, this green cornstarch thing that kept chasing Bartholomew, and Bartholomew wanted to, protect his kingdom. So he basically, the story is that, he protected his kingdom against this, green gooey mess, which was actually cornstarch. Okay, so this is the literary background of cornstarch. But anyway, so why do they do this? And I told you that, so if this is what cornstarch particles look like, if this is, if you're applying flows, then all the particles start aligning, so they flow easily. So if you plot the viscosity versus the shear rate, initially the viscosity is constant, then the viscosity reduces at very low shear rates, because that is where you're gently stirring it, and then at very high shear rates, at very high shear rates, they all jam into each other, very much like that traffic jam in the bus. Okay, or either the human jam in the bus or the traffic jam on the roads. And actually, people look at traffic jams, okay, because the same, the same kind of models that can actually explain traffic jams can also be used to explain coffee stains, which I'll tell you about later. Okay, that also has a lot of rich physics going on. Okay, so this is why you feel that way. Okay, and this plot versus viscosity versus shear rate is what is called a flow curve in these materials, because in water, if you apply a shear rate, no matter what shear rate you applied, viscosity would be constant, right? But for all the soft materials, they change, and it is these changes that we study, and we try to modify our engineering these materials so that their viscosities or their elasticities they change in useful ways. Okay, so fine. Now something else. You all, okay, monkey business. Okay, these materials, soft materials, can also climb like monkeys. Okay, so here what I have is a polymer. It's like plastic. It is polyethylene oxide. Okay, so this is all stuff that you can get, I mean, very easily from any chemical store. Okay, and just mix it in water. And so what we'll do is, we mixed it in water, and this I do not have a video, but then I just had water, and I put a drilling gun inside, and I just I rotated I spun the drilling gun very, very rapidly. And this is what is your meniscus going to look like? It's going to be convex downwards, right? You know that. Why is that? Centripetal force. It's just getting thrown out, right? But then polymers do something completely different. And this is again something we did in our my two students. Okay, so this is called a Weisenberg effect. So when you spun this thing, okay, the drilling gun in your water was getting thrown outside, right? But when you do the same thing for a polymer, you'll see that the polymer will actually climb the drilling gun. Okay, and that is why we are saying that it behaves like a monkey. So let me play this. Oops. Wait, this is not playing. I'll just do it from here. Oh, it's not playing here. Oops. It's not playing. Okay. So maybe should I come out and show you the thing? Is that okay, Sumathi? Can I come out of the presentation and show this? Okay. Just. Okay. So, sorry? Oh, okay. That's bad. So somehow it is. Huh? Oh, is he? Okay, okay. So I'll just play it anyway. And that's what I'm trying to show you. So see, when you stir water, your meniscus is curved this way, right? With the meniscus, with the water being at the highest level near the, near at the wall of the beaker or whatever you're stirring it in. But when you stir a polymer, it goes up the rod. It actually climbs the rod like a monkey. Yeah. So we're trying to play that. No, this is something, so like I told you that the flows of these materials are very complicated. So it's playing now, is it? Oh, lovely. So thank you. So I'll tell you why it is happening. Yeah, it is because these materials are elastic as well as viscous. So look at this. It's starting, huh? So this is, we've just colored it red so that you can see it. And we are taking the same drilling gun and we are just, spinning it. And can you see it going up the rod? Huh? Why does that happen? Because unlike water, polymers have elasticity, right? So when you're spinning the water, you have lines of flow, right? But the lines of flow, they are not viscous. They have elasticity, right? So they are really like elastic bands. They are like rubber bands. Okay, so and what do rubber bands try to do? They try to contract, right? So that's exactly what's happening. The lines of flow are trying to contract, and as they contract, they're just pushing the material up the rod. And this is actually a very modest flow. You'll see stuff on the internet. So this is called Weisenberg effect, after Weisenberg, who first noticed it and explained it. So there are movies on the internet where they've kept like a meter scale next to it and it goes up a meter. Okay, so it has to be just the right amount of elastic and viscous for this to happen. Okay, idli batter does it, and for all those of you who don't have idli, you can try it with pancake batter. Okay, maida and egg yolk and a little bit of water and maybe some milk. Okay, you just need the right concentration and you'll find everything on Google now. You can actually do it. You don't even need a drilling gun. You can just, if you can shear really, if you can spin it really, really hard, it'll work. Okay, so let's go back to this. So I hope now, I don't know if this will now work, these things. Okay. Okay. No, I think I'll have to go back for everything. And there's maybe I'll just then, do it from outside, because the videos, if they're not working, it'll be better to do them here. Okay. Okay. There is also something called dye swelling. Okay, how much time do I have? 8 minutes. So maybe I'll just do this and stop, and then we'll go on to other things after coffee. Okay. So suppose I have I have say a bottle of water. Okay, with a small orifice. Okay, and then if I turn the bottle around and I pour out the water, the thickness of the water stream is going to be same as the orifice, right? But not so for that same polymer which was climbing the rod. And that is all, I'll tell you why. Okay, so this is what is called a Barros effect. So this is what it does. Barros. Okay, again also done in the lab. Okay, so the same polymer, and you're basically trying to squeeze it out of a bottle. Can you see that it is swelling? So it's at the point where it is exiting, it is actually thicker than the size of the hole through which it is falling. And why does that happen? Because these are polymers, right? And polymers, the solvent is very important because polymers have lots of hydrocarbons, right? So in water, they really don't want to be in contact with water, right? That increases their energy. So polymers form globules, okay? So if you had a bottle like this, okay, with polymers, okay, so this was the nozzle. Okay, so if you had polymers and this is all water, and if you put polymers here, they'd all be, like kind of, you'll find them as small globules because that is how they can minimize the surface, the area of contact between themselves and the water. Okay, so they are all like this. Okay, so you can think of them as like, little round, globules. Okay, now the moment you're squeezing it out, so remember this part is a little thinner, right? But then these globules many of them have to go through it. But these are very fragile materials, right? So they can change their conformation very easily. So over here, they become like chains. But the moment they come out, okay, then there is no confinement on them, right? So then they go back to being globules. Okay, and that is why they swell. So again, so what I showed you here, this was a very, very modest swell. Okay, but there are places where, it can swell up to like 3 times, 4 times. Okay, so maybe I can go to another one. So, okay, so this I'll stop. And I've forgotten what my next video was. Keynote, not this one, the other one. Okay, this is great. Now I can't find my video. So this was spontaneous swelling. Okay, you didn't do anything, it's just the fact that, there was a confinement and then you remove the confinement, it just swelled spontaneously. Now another thing that these materials do is, okay, dancing shampoo, they can dance. Okay, so let's see this. So this is true for, you can see, you wouldn't see it because, this is happening at, much faster than what your eye can resolve, but this will happen. Okay, so you can do this with shampoo or, even lotions. So let's see. So this is called the K effect. Okay. This is all from YouTube. Okay, so if you have an inclined plane, okay, and you're just dropping some shampoo, okay, so suddenly, do you see these strings? It's not just flowing down, in the same way, but you see these lassos and these, strings that come out. And why does that happen? Because, see, these are shear thinning materials, right? Their viscosity goes down because they are flowing, right? Because going along an inclined plane means that there's a shear rate that is acting upon them, right? And so what happens? So this is flowing down, and as it flows, the viscosity is changing. And there's also a slipping on the top layer, okay? So really there is a gradient of viscosity in the shampoo. Okay, so these lassos coming out, this is exactly how ice skaters actually skate on ice, So they're coming down rapidly, and then they just, they just encounter a dimple in the the slope, and then they just go, flying off. And that's exactly what's happening here. Okay, so this is called the Fay effect, and believe it or not, people have written serious papers on these, that have been published in very, very good journals. Okay, so maybe I'll go to granular matter after the break, but I'll quickly tell you another thing, which is a siphon. So you know that, if you want to siphon out water, okay, your siphon has to touch the water, right? There is no action at a distance here. Your siphon has to touch the water, but not so for the polymers. Okay, so I'll just, this is called the Fano flow effect. So this is called a tubeless siphon. So you can actually siphon out polymer without touching the polymer. Okay, but you have to watch it a little carefully. Fano. So this is again, I think I'm showing you a YouTube video here. Yeah. Okay, so can you see? So, so you're just pulling out the polymer, okay, and if you if you want me to play it again, I can do it, but then you see that the syringe is filling because, there are those markers that tell you about the volume. So actually they'll do it for many. So, depending on the elasticity of the material, look. So I was telling you about why these things happen. So like I told you, flows of soft materials, it is, you have to treat them tensorially. So you have tensors, right? So basically, you have these 9, it's like a 3x3 tensor. And so this is, I think, just egg yolk. It doesn't go up much, but it does go up a little bit. Because if you look at the syringe, it's actually constantly filling up. So material is actually transporting from your, the bottom into the syringe. And this one is, I think, huge. So this is just, again, the same thing that we were using, which is, dyed polymer PEO. Okay. Anyway, so so you can do this. Now, as I was telling you, you see all this because soft materials, you cannot describe their flow in a very simple way. You need a 3x3 tensor. Okay, so that tensor will basically, tell you. So because in soft materials, if you apply a force in one direction, the deformation could actually be in a different direction. Okay, so you have these 9 components that you have to think about. Okay, so what I just showed you earlier, with that Weisenberg effect, the rod climbing, okay, that is because of something that normal liquids do not have. And that is what is called the normal stress difference. So if you put water, what is the normal stress? It's just pressure, right? It's just pressure. And pressure, it's hydrostatic, it's isotropic. But pressure is not isotropic, it is not hydrostatic for these materials. And that is because these fragile structures, they have these very, very complex configurations which are also very sensitively dependent on the dynamics, or rather the other way around, that the dynamics are very sensitively dependent on the structures, right? So you have this very, very complicated, tensor that you need to be able to describe all of this. And what is this tubeless siphon? This is a little more difficult to actually explain using a stress tensor or a strain tensor. But what this is, these materials have a property called extensional thickening, which is that when you stretch these materials, they start behaving like a solid. Okay, so that is called extensional. It could look like a liquid, but suppose you could just take a little bit and you just stretch it, it looks like a solid. Have you seen bhindi? Bhindi. So you take the, that inside that, gooey stuff out of bhindi. Try to stretch it. Huh? It will actually thicken, and not just that, you'll also see pearls. Have you seen? That's an instability. So if you take bhindi between your fingers and you try to stretch it, you see these pearls that develop. This is a kind of instability, and that's a viscoelastic instability. Okay, and where else it happens? In our neurons. Okay, so that is actually, people are saying that, if you can stop these instabilities, you might actually have a cure for Alzheimer's. Because when you stretch nerves, okay, they show this instability, which is called a beading instability. Okay, so, so at least, you may not cure Alzheimer's, but at least you can find out why they are happening. Right? And that is why we do our experiments, as model systems. So once we come back, I'm sorry, I'm almost done, but not quite. So, I was telling you more about colloidal systems till now, but now I'll tell you about sand a little bit. I have another experiment that I want to pass around, and then I'll tell you why coffee stains are rings. Okay? Okay, thank you for your attention, and see you after coffee. We'll do it all at the end, maybe, yeah. And we also have the after dinner session. So believe it or not, we'll do some sums based on these. And also from the falling ball experiment that you did, which I know didn't work very well. So the viscosities were totally off. But then I would take that as a chance to discuss about, sources of errors in experiments. That's also important, right? Okay. Thank you.